I just received this crazy email. Wait, I'm being recorded. I just received this lovely email. Oh yeah, I forgot this is being recorded. I'm gonna tone it down, tone it down. Just wait for Paul to get back. Andre unfortunately has a meeting, so he's going to miss this. Oh, we got lots of time. I can do this talk in 10 minutes if need be. I'm going to be stretching it out. Yeah, this talk has the record number of slides for an APS. APS talks are usually 10 minutes, so you have 15 slides, and I've got 45 in. But I'll move a little more slowly. Thanks, Paul. Great. Yeah, no, it's fine. Beauty. Very good. Okay, so this started as an amusing story. So I have this clip on time warp that you can see on YouTube if you look under bouncing drops, or gotas como nunca has visto, something like that. Yeah, and so and it's basically looking at these bouncing drops. And in response to this, I get lots of crazy emails because of this clip, including I got one yesterday from Grace the Wonder Girl. So. I got an email from Rosie Warburton, and she said, "Your experiments are proof that God exists." And when you get really interesting emails, you have to respond just to see who's sending them. And so I responded to Rosie, and I said, "Well, thank you very much." And in her second email, she said, "I have seen exactly what you describe in my Tibetan singing bowls." Okay, so this is Rosie here.
At this point, you don't know what a Tibetan singing bowl is.
No, exactly. I didn't know what a Tibetan singing bowl was, although I'd seen something similar once. But she has a sound healing, a sound health center where she takes advantage of the medicinal value of the Tibetan. I'm being recorded. No, but it's quite real. I should just stop talking. Stop talking. Yeah, I think this pretty much says it all. So, but in any case, the idea is that there's some sort of resonances excited, which can be good for your health. Okay, so let's just leave it at that. And so I got curious, and I was wondering, to what extent, what can you actually see in these Tibetan singing bowls, right? So I said, can I have one? And so I bought one. And this is the story of the Tibetan singing bowl. So these were have been used by sort of shamanic cults in Tibet, in the Himalayan region, Himalayan fire cults, they say here. And so they're composed of metal alloy plus traces of meteorite, the original ones, and they're used for all sorts of things. Healing, exorcism, chakra adjustment, shamanic journeying, and levitation, okay? So the question is, when we think of levitation, we think of, but we're going to see that they can levitate drops, okay? So that's a step in the right direction. And so apparently when China went into Tibet, a lot of these bowls were removed because they had some religious significance. And so this particular bowl that we see here was imported to Texas, and then Rosie purchased it in 2000, and then we got it sent to us in 2010. Okay, so here is the here's the Tibetan bowl. So it's about that big. We got actually a series of them. But you can hear it. So you rub it, and you see the interface break and drops being ejected. Which is, you know, by rubbing your finger on a wine glass, you can get waves. But these waves are breaking, right? So it's because the metal is actually much more malleable than glass. So you get this large amplitude wave, large amplitude vibration of the bowl, which excites waves, and the waves break and release droplets onto the surface. And so, what?
It's hard to imagine that metal is more...
It is. Well, we can actually compute, with the theory, we can compute the Young's modulus of the thing and see what it's made of. So that's something we did. Good quote from Rilke there. Okay, right, so there are variants on singing bowls. So these are the 4 that we purchased from Rosie, one of which is now in the living room of Yves Couder. So, so this is the Chinese, exactly. So I'd seen this one. So this one, they have handles, and you rub them. You fill it with water. You rub the handles, and that excites the resonant modes of the bowl, and occasionally you'll get drops breaking. It's not as efficient.
Yeah, you have to work a lot harder.
Exactly. This is really quite hard work. And the other thing is, as we know from the course, is if the water gets contaminated, if you put your finger in it or something, you always have oil on your finger, and then you get surfactants, and that will kill everything, right? So we have the different we have the French singles, the French singles, but it is quite true. By rubbing thing, you basically excite modes of vibration, and these will excite waves, but they will not break, right? The waves won't break, that's to say. And then we have the American singing bowl. So we actually used these. We used all of these in our study. So we just took the top off Red Bull, and because we wanted to get to a regime where you get really large amplitude vibration. Okay, so the mode you're basically seeing and the mode that you're hearing with that excitation is the 2-0 mode. So basically, these things are short and squat, so you don't get variations along the height. You just get basically an axis. Well, you get something where the variation is just a function of radius. So you basically just have these modes. Okay, so you can get higher modes such as these, but the dominant one you get, and the one that we're going to excite acoustically, is this one. Okay. So these are different modes excited in a wine glass with different frequencies. Okay?
You see the kidney-shaped line?
Sorry, what was that?
You see the kidney-shaped line algebraic curve?
Sorry?
It's the product of 2 ellipses.
Oh.
And if the perturbations, they split into 4 kidneys.
All right. Okay, so right, so what we did is we wanted to look at this in a controlled way. So rubbing it with the stick is not a controlled way, and either is giving it a bang. So what you can do is look to see what the resonant frequency is just by hitting it. So by hitting it, you see that you excite various modes, right? The 4-0 being the dominant one on this particular bowl. By rubbing, you're basically exciting the 2-0, which is this mode. Okay. So what we do is for any given bowl, we do this, and we can then see at what frequency we want to excite the thing is most susceptible to. So then we force it acoustically. So we put a loudspeaker beside it and excite whichever mode we want. And in these, it's basically...
So probably monks take all their lives in order to...
Get this right? Yeah. I don't know if they take power spectra. So you can, if you look at this, so the speed of sound in a bowl is basically Young's modulus divided by density, square root. And so this is the speed of the bending waves. Depends on the speed of sound. And so then you can see that the frequency that you hear goes as bowl radius to the minus 2 power. So basically, as the bowl gets smaller, the frequency goes up, and that's consistent with what one you get an idea of that when you play around with several bowls, and also so the frequency is increasing with the mode n squared, and we see this also in the data. So f is going as n squared. So we can sort of rationalize the acoustic response of these bowls or these wine glasses. Okay, and so AP French, who wrote lots of great physics textbooks, right? Probably take it. Yeah, he did some. He looked at this problem. He was at MIT, and so he has a book on. I did French relativity. Yeah.
I think he wrote like first-year physics books too, right?
Yeah.
I used his book when I first learned physics.
And so basically, if you describe the system, you think of the system energy, you have a kinetic energy associated with the vibration of the wall, and then you have a potential energy, and this is associated with the bending. Okay? So that's proportional to the amplitude squared. That's the time derivative of the amplitude. And so from this, basically, you can infer the frequency, which is basically the ratio of these two coefficients. So using this approach, you basically calculate the dependence of the vibrational frequency on the system geometry and the Young's modulus, y. Okay, and so then if you fill the thing with fluid, you're changing the inertia, so you then have to consider the inertia of the fluid, and so it changes the frequency. In particular, you see that the frequency decreases as you increase the depth. Okay, and this is, so his model is basically consistent with what we see in the bowl. Okay. What's that? What's it called?
So you put a lot of glasses.
Oh yeah, we're going to see that. We're going to see that in a second. Yeah. Yeah, I have a great video of that. Okay. It's the glass harp. This guy's pretty good. So we have a range of different size glasses and then filled to different levels. So each one will have a different frequency.
This works better with crystal glasses, right?
Mm-hmm. With which glasses?
Crystal.
This is probably crystal.
Yeah.
I sense that this guy's optimized the system. Yeah, exactly, right? Exactly.
I mean, you have to work hard with a regular wine glass to get it the same. Right?
You just have to get this. There's some sort of stick slip mechanics,
That's right.
right?
That's right. So you gotta get the right thing on your finger.
Yeah. Okay, so that's basically just the acoustics of the vibrating bowl, and the acoustics of the vibrating bowl filled with water. But what about this fracture of the surface? Now, this is basically rooted in the Faraday instability. And this arises when you have a fluid layer and you shake it from below. And you basically shake it so hard that the acceleration associated with the shaking exceeds gravity. Right? In fact, it goes unstable when the forcing acceleration is about 4 times that of gravity. And so then when you cross this, there's a critical threshold, and the critical threshold is going to depend on the surface tension, the viscosity, and the depth of the fluid. But when you cross this threshold, the surface goes unstable to a field of waves. Okay, and these are called Faraday waves. And these, so this is the forcing parameter. So that's a forcing frequency. That's a forcing acceleration. So that's basically the so it's forcing amplitude. So that's basically the forcing acceleration over g. And again, it goes unstable when this thing exceeds something around 4. Okay, and so that's forcing like this. But that's not what we're doing in the experiment, right? We're being forced by this vibration, but happily the same, this is also described in Faraday's first paper in 1831. So he basically put a wall in and vibrated it back and forth, and you get the same characteristic waves generated in the vicinity of the plate. Okay? So that's basically the mechanism here is you're getting edge-induced Faraday waves. Okay? And so we can now characterize the system carefully through a series of experiments, because we can now, we basically put a loudspeaker beside the bowl and force at the resonant frequency, which we can get just by hitting it and measuring the spectrum. And then we have an accelerometer here, so we can measure the amplitude of the wall movement. And so basically that sets the the dimensionless acceleration. So now we're going to define a dimensionless acceleration not in terms of the vertical amplitude, but the wall amplitude of the wall vibration. Okay, and so this again measured with the strain gauge, and so we can basically look at the progression of the system. So how does the flow change as a function of this dimensionless forcing parameter? So here we see as the forcing acceleration increases, first you just see these ripples. As we increase, we have larger amplitude wall vibrations. You get these sort of edge waves forming. Things are slightly confused. Yeah, just to make it easier to see. And of course, that does introduce complications in the meniscus, but this is just qualitative. But then you see really quite large amplitude waves here. And things are basically two-dimensional here. Now they're really getting quite strongly three-dimensional. And at the highest forcing, the interface will break, giving rise to these drops, which bounce along the surface. So that was effectively what we were seeing in the first video. Okay, so if we go through the same progression again, looking from above, we have the top left, we have these sort of edge waves propagating in. As we increase the acceleration further, we start developing a three-dimensional structure, which becomes more pronounced. And then eventually leads to violent motion along the edges and the generation of droplets. So interfacial fracture. So it's interfacial fracture through vibration. Okay, and so again, same progression. We zoom in towards the edge. Here you can see the second, you see the edge waves forming. See the Faraday waves generated near the edge, and then. What's that?
It's a lot like the program.
Yeah, exactly. And then, gotta get to do this with your program. But then, so you can see these things, these waves breaking here and ejecting drops onto the surface. So this is again all being prompted by Rosie's email, but so you can then, so there are scaling arguments around for the critical forcing threshold at which you get Faraday waves, and we can compare this, and this is basically consistent, our data is consistent with existing theory, and similarly there's a critical threshold at which the interface breaks, and that's given here, and this is actually pretty easy to see how it works. You simply say, so criterion for interfacial fracture through shaking, you basically know so basically we know that we're going to excite Faraday waves, and the question is whether this Faraday wave breaks, right? So we're accelerating up and down with an amplitude gamma, and basically, so we know this wavelength is a Faraday wavelength, and we know how that depends on the forcing amplitude. So the question is whether this blob, the inertia associated with acceleration, so if we know the characteristic size, we know its characteristic mass, right? So the force acting upwards in the stage of mass, largest acceleration is going to be m gamma. The question is whether that is bigger than the confining surface tension force. So that's going to go like surface tension times its perimeter, so gamma times 2 pi lambda f, okay? And so that's exactly where this criterion for interfacial fracture comes from. And again, gamma is actually much greater than g, so you can just throw g out of the equation and just worry about this because the largest acceleration is coming from this. So that's the criterion for interfacial fracture, and that's again consistent. Our data is consistent with that criteria. I will not mention the quantum analog, because I'm being filmed. Okay, and so, yeah, so there's also scaling for drop size distribution. And so this is basically all of everything we see in terms of Faraday threshold, interfacial fracture, and droplet size distribution is consistent with the stuff which is already in the literature with this kind of acceleration. Okay, so what about levitation? This is...
How loud does this, I mean, can you be in the room?
Yeah, it's not so bad. Yeah. And what about levitation? So that's again one of the pluses of the Tibetan singing bowl is it assists in levitation. So so here we do see a drop being levitated in a Tibetan singing bowl. So here's the edge of the bowl. It's vibrating, and there's the drop, which is happily bouncing. It will bounce forever, right? But what we really wanted, so here's another image. So a slightly larger amplitude, but again, you can sustain them. Again, the whole secret for levitating drops, for bouncing drops on the surface, is that the contact time be less than the time it takes for the air layer between the drop and the bath to drain. Once it gets about 100 nanometers, then van der Waals forces come in to play, and they initiate the coalescence. So this is a time series where you see the motion of the bath and the motion of the drop. So here we see large amplitude bouncing. This one's almost period doubled. Once you get it to period double, you should be able to get it to walk. But we couldn't. Okay, and so what was motivating this was these experiments by Yves Couder, which demonstrate that drops walking on the surface behave like quantum particles by virtue of their accompanying wave field. So there's sort of a wave particle duo which moves around and exhibit all sorts of peculiar features. And so we were really hoping to see this in the Tibetan singing bowl. But that was perhaps a little too much to ask. So, and so why doesn't it work in the Tibetan singing bowl? Well, Tibetan singing bowl, remember, we're getting oscillations like this. So they're basically 4 nodes along the edge, and then there are 4 regions where you get, where the edge is moving a lot. And so you have these regions where there aren't waves, and so the things can't walk through there. So basically, the sort of, the criterion for walking is going to be satisfied in some regions but not others. So you're not going to be able to get the thing to move continuously throughout the domain. So you can be above threshold in certain regions and below it in others. and in these to get walkers, you have to get very close to the Faraday threshold, as to say to the threshold at which you generate waves everywhere on the surface. And again, that will not be possible here everywhere simultaneously. So, but we did try different, we tried to get larger amplitude oscillations by using these thinner cans, but still we were not able to get them to walk. I don't think it's impossible, but we didn't get there. So, right, so we've looked at these things. We've seen the basic physical mechanism is the oscillation, the natural vibration of the bowl, exciting edge-induced Faraday waves, which then break and give rise to drops. And we've got them to bounce, but not walk. So they're good for levitation, bad for quantum mechanics.
Sometimes you see droplets. I mean, you see them, but I mean, it's happened, and maybe your eye just can't tell. But even if you have a coffee. Sometimes you get a droplet that forms a
definitely.
And it seems to slide along
Definitely.
without bouncing.
Definitely. Oh, no. So what's happening there is it's actually decreasing in size. So it's going through this coalescence cascade. It starts big, then it decreases in size. Right. As it does so, it's rolling. But it's basically dumping half of its contents. But I have a espresso maker in my apartment here in Rio. And it's really, it releases 1 drop of hot coffee per unit time, and so it really so it's basically landing 1 at a time. And if you have cold milk, then it really so that's a way to levitate drops, right? If there's a temperature difference, because we'll see this. So if you have a hot, let's think about this. If we have a hot drop on cold, so the one way it works and one way it doesn't. So if it's cold, hot, what happens? So that means this is hot, this is going to make this hot, which means that the surface tension is going to be low, right? Relative to that, which is not what you want, right? Because that's going to drain the air layer. So what you want is cold. So a milk drop on coffee. I think maybe I heated up the milk in the microwave beforehand. But then you have the opposite, right? So then you have the Marangoni stresses flux fluid into the gap, right? So that's going to make, they're going to last much longer. So you have a cold drop on a hot surface, then you get you're going to enhance the ability to levitate. But again, but eventually the thing merges.
There's an effect with cold water and hot water.
Yeah, yeah. And so, but once it merges, then so this is what you don't see with the naked eye. These retract at very high speed, and then you get these capillary waves. These capillary waves are transferred upwards, and the associated momentum transfer causes the thing to lift off. So it dumps half its contents, lifts off, and then goes through the same thing again. And so that's when you see the coffee drop rolling along the surface, it's basically decreasing in size. And you see the same at the beach if you throw water across. So right, so that was the story, which I managed to stretch out for half an hour. So, but I like the last quote here. That's what we got. Yeah. So this is. Last summer I was in Paris and I got an awful cold and I couldn't do anything but read for 2 weeks. So I went and read War and Peace in the Luxembourg Gardens, and this is a great quote. Bizarre, huh?
What was he? So
It was totally
Tibetan singing.
no. It's a scene he's talking with.
What's
you know
the
that
scene?
when
What is
you know Kiratayev, who's the peasant.
Yeah.
It's right after his death. Pierre has this dream.
It's a globe, like it's a.
This is a dream. This is basically Pierre is having a dream right after his friend dies. And there's an old teacher talking to him, and so the teacher shows him. It's totally bizarre, but very bizarre in the context of this research.
You actually prove that God exists, right?
Yeah, right. But it was very interesting, and we showed Rosie some love because we had an interview with BBC. So this all started from Rosie's email. She visited the lab actually. She's very, very nice woman. Very brave. Her son's working with that. Very famous by.